Assalamualaikum. This is 12th chemistry, and our today's this lecture is about reduction of these carbonyl compounds, that is aldehydes and ketones. As far as this reduction of these carbonyl compounds is concerned, the reduction of these compounds, it can be carried out using different types of reducing agents. Like we have got reduction to alcohols, we have got reduction to hydrocarbons. And now, as far as the reduction to alcohols is concerned, now aldehydes and ketones, both these aldehydes and ketones on this catalytic hydrogenation influence of various reducing agents, like we have got nickel, we have got this palladium, or we can use lithium aluminum hydride, or we can use sodium borohydride. So when these reducing agents are used while carrying out the hydrogenation of these carbonyl compounds, the products obtained, the products obtained are alcohols. Now you can see here, this is acetaldehyde when it is reduced using this platinum, or we can use any of these reducing agents. For example, platinum we can use palladium, nickel. So the product obtained is this primary alcohol. You can see in case of these aldehydes, they give rise to the formation of these primary alcohols. This is ethanol when this acetaldehyde it is reduced using any of the above reducing agents. Similarly, as far as ketones are concerned, when ketones are reduced, they give rise to the formation of these secondary alcohols. You can see this is acetone when we reduce it using this lithium aluminum hydride. This is LiAlH4. Now we get we get propan 2-ol. We get, in this case, we get propan 2-ol is formed. Now this is when we use these reducing agents, that is this lithium, this nickel, platinum, palladium, lithium aluminum hydride, or sodium borohydride. Now, as far as these reducing agents are concerned, I have told you that these reducing agents are very effective reducing agents. Now, in case of these unsaturated aldehydes and ketones, where we see there is unsaturation, there can be double bond. Now, this as the carbonyl gets reduced, we see that this double bond may also get reduced. So in order to reduce these aldehydes and ketones which have got these unsaturation, or which have got a double bond, so in order to reduce them selectively, that is only to reduce this carbonyl group, we use and to prevent this reduction of this double bond, then we use a reducing agent, that is hydroborane is used, has been suggested. And what is the function of this using this hydroborane is that it prevents the this reduction of these unsaturated these sites, that is double bond, is the reduction of double bond is prevented, but only the reduction of this carbonyl group takes place. So in order to prevent the reduction of this double bond in case of unsaturated aldehydes and ketones, we use this borane is used. This is also, we call it as BBN. Now then we have got and then we have got another type of this reduction, that means when reduction to hydrocarbons. Now, as far as this is concerned, now in this case we see both aldehydes and ketones, they are reduced to the corresponding these hydrocarbons. Now in this case we have got one of the reducing agent that we use, that is zinc amalgam, and this concentrated hydrochloric acid, or concentrated HCl. So this reduction is known as Kalman-Son's reduction. So in this reduction, so when the reduction of these carbonyl compounds, that is aldehydes and ketones, is carried out using zinc amalgam and concentrated this HCl, then this reduction is known as culmination reduction, and in this case we see that these carbonyl groups, they are reduced to the corresponding hydrocarbons. You can see this is acetaldehyde. Upon this reduction using this zinc amalgam and concentrated HCl, it gets reduced to the corresponding alkane, that is ethane is formed in this case. Similarly, this is acetone. Upon reduction, when it is reduced using these reducing the under through this in this culmination reduction, we get it will form propane. Here you can see here acetone gets reduced to the corresponding alkane, that is propane. Similarly, this is acetophenone. Now as far as acetophenone is concerned, when the reduction is carried out in this culmination reduction, that is using zinc amalgam and concentrated HCl, we get this is ethyl benzene is obtained in this case. Now this is when the reduction is carried out in through this culmination, this reduction using these and using this zinc amalgam and concentrated HCl. So now we can also carry out the reduction of these carbonyl compounds using basic solution of hydrazine. So this type of reduction, when a basic solution of this hydrazine is used, it is known as Wolff-Kishner reduction. Now in this reaction, we see both aldehydes and ketones, they are made to react with a mixture of this hydrazine and strong base, that is potassium hydroxide or sodium hydroxide, or we can use potassium tertiary butoxide at a temperature of this 400 this is 53 to 473 Kelvin in a suitable solvent, that is ethylene glycol, or simply we call it as glycol. Now here both these aldehydes and the reaction it takes place in two steps. So in first step we see both aldehydes and ketones, they form hydrozones, and which on this treatment in the second step with this strong base, that is potassium hydroxide, they give rise to the formation of these hydrocarbons. You can see this is acetaldehyde or ethanol. When it is treated with this hydrazine, in first step it gets converted to hydrazone, and in the next step using this strong base, that's potassium hydroxide, at a temperature of 453 to 473 Kelvin in this solvent, a glycol solvent, the ethylene glycol, it gives rise to the formation of this corresponding hydrocarbon, that's ethane plus nitrogen gas is evolved. Similarly, when acetone or propanone, it is subjected to this Wolff-Kishner reduction using these reducing agents, that is this hydrazine, basic solution of this hydrazine, and this acetone, it gives first to rise to this is hydrazone is formed. And hydrazone on further this treatment with this base, it gives rise to the formation of this corresponding hydrocarbon, that is this is propane, and then we have got this nitrogen gas is also evolved. Then similarly, as far as this acetophenone is concerned, this is acetophenone on reaction with this basic solution of this hydrazine in this Wolff-Kishner reduction, we see it gives rise to it gives first rise to the formation of this is hydrazone, and which on treatment with this base, it gives then we can see here this is ethyl benzene. Now plus nitrogen is also evolved. Now then we can see this reduction with this hydrogen, when the reduction is carried out using this hydrogen iodide in presence of red phosphorus. Now this reaction is carried out by treating these carbonyl groups, that is aldehydes and ketones, with red phosphorus at a temperature of 423 Kelvin. Now in this case we see again these carbonyl compounds, they get reduced to the corresponding these hydrocarbons. This is acetaldehyde. When it is treated with hydrogen iodide in presence of red phosphorus at a temperature of 423, this acetaldehyde or ethanol, it gets reduced to ethane, and water plus iodine is also given out. Similarly, we can see here this is acetone. Now acetone, which on treatment with this hydrogen iodide when treated and red phosphorus, it gives rise to the formation of this is propane, water and iodine. So this is when the reduction is carried out using red phosphorus. Then we have got a reduction to pinacols. Now as far as this reaction is concerned, in this reaction we see both aldehydes and ketones, these carbonyl compounds, they are treated with this magnesium amalgam with and water, and they get reduced to corresponding these diols and pinacols. Now in this reaction we see only these ketones, they show this reaction, whereas the aldehydes, they do not undergo this reaction. You can see here, this is two molecules of acetone I have shown here, that is this is propanone, and this is also propanone. They are the two molecules, and they are, when they are reduced in this using this magnesium amalgam and water, they give rise to the formation of, they give rise to the formation of symmetrical diol. You can see here, this is 2,3 dimethyl 2,3 butane 1 butane 2,3 diol. So in this case we see pinacols are formed. This is when the reducing agent is reducing agent user is magnesium amalgam and water. Then we have got a ring substitution reaction in case of these aromatic aldehydes, you can see, or and ketones. Now as far as this ring substitution is concerned, in case of these aromatic aldehydes and aromatic ketones, we see that this is an electrophilic substitution reaction, and in this case we see, since these aldehydic group and ketonic group, both are, they are deactivating groups, and they decrease the electron density at ortho and para positions. So obviously the incoming electrophile will not go to these positions, it will be directed towards the meta position. Now because this meta position, it is not affected, rather only these ortho and para positions are affected, because the electron density gets decreased at ortho and this para position, because this aldehydic group and ketonic group, they are the electron withdrawing or deactivating groups. Now as far as halogenation is concerned, this halogenation of this benzaldehyde, when it is carried out using this ferric salt, you have got ferric chloride. Now the product obtained is, it is a metachlorobenzaldehyde. Similarly acetophenone, when it is halogenated, or when it is halogenation is carried out using this ferric salt, we get this is metachloro acetophenone. Now similarly, as far as then the another type of this electrophilic this substitution is, that is nitration. Now this nitration is carried out using a mixture of concentrated this nitric acid and concentrated this sulfuric acid. Now here we see that benzaldehyde, upon this nitration, it gives rise to the formation of this is meta-nitrobenzaldehyde. Similarly acetophenone, upon nitration, it gives meta-nitroacetophenone. Now then we have got another this electrophilic substitution reaction, that is sulfonation. Now this sulfonation is carried out using concentrated this sulfuric acid. Now in this case benzaldehyde, when it is sulfonated, or when it is subjected to sulfonation, it gives this benzaldehyde metasulfonic acid. Similarly, when acetophenone, it is sulfonated, it gives rise to the formation of this is acetone metasulfonic acid. So we see in these ring substitution reactions of these aromatic aldehydes, the incoming this electrophile, it is directed to metafusion, and I have told you why. If we look at it as at the canonical structures of this benzaldehyde, we see the electron density gets relatively, it gets decreased at ortho and para positions. So hence this incoming electrophile doesn't go to these positions, although we see the reaction mixture contains a small amount of this ortho product is also formed, but the major product of the reaction is meta product. So this is for today. Thank you very much.